Bismillah ar-Rahman ar-Rahim. In probability theory, we have the Markov and Chebyshev inequalities. If random variable x is non-negative and y is a positive real number, the probability that x is greater than y is upper bounded by the expectation of x divided by y. If x is a random variable with finite variance, the probability that the absolute value of x minus the expectation of x exceeding positive y, this probability is upper bounded by the variance of x divided by y squared. The goal of this video is to develop matrix versions of these two inequalities. Now x is an n by n random matrix, a matrix whose elements are random variables. We take x to be Hermitian and positive semi-definite. We have a non-random matrix y of size n by n. It is assumed to be Hermitian and positive definite. If we go back to the conventional Markov inequality, it can be written in the following way. The probability that y minus x is strictly negative is upper bounded by the first moment of x divided by y. In the matrix case, this event y minus x strictly less than 0 is replaced by the n by n matrix y minus x being not positive semi-definite. X and y are Hermitian matrices, so y minus x is Hermitian. A Hermitian matrix is not positive semi-definite if it has at least one strictly negative eigenvalue. In the Chebyshev inequality, the event can be written as y minus the absolute value strictly less than 0. The equivalent event in the matrix case is that y minus the absolute value of this matrix, x minus expected x, is not positive semi-definite. The expectation applied to a matrix, or the variance applied to a matrix, is an element-wise operation. That is, we compute the expectation or the variance of each element or component in the matrix. What does the absolute value mean? If A is a Hermitian matrix, then A is unitarily diagonalizable. The eigenvalues of matrix A are purely real. We can write A as Q, a unitary matrix of eigenvectors. Q Hermitian Q is equal to Q. Q Hermitian is equal to identity of size n by n. So this Q Hermitian is the inverse of Q. Big lambda is a diagonal matrix. It has the eigenvalues of A on the main diagonal. I will assume that the eigenvalues are in a non-ascending order. So lambda 1 of A is the maximum eigenvalue. Lambda n of A is the minimum eigenvalue. Going back to our question, what does the absolute value operation mean here? It means that we construct a matrix with the same eigenvector matrix Q as matrix A. The eigenvalues are replaced by their absolute values. Note that if A is Hermitian and positive semi-definite, the eigenvalues are real valued and non-negative. The absolute value of A is equal to A. In a similar fashion, we can define the matrix square root of A and the matrix reciprocal square root of A. For the square root, denoted by A to the power 1/2, we use the same matrix Q. We replace the eigenvalues by their square root. Here, we restrict A to be a positive semi-definite matrix, so we are taking the positive square roots of non-negative numbers. A to the minus half is defined for a Hermitian positive definite A with strictly positive eigenvalues. A to the minus half is Q Hermitian. Between them, we have this diagonal matrix of eigenvalues. These are the eigenvalues of A raised to the power minus half. The objective here is to show that in the matrix case, these upper bounds in the Markov and Chebyshev inequalities are replaced by these upper bounds involving the trace of y inverse times the expectation of x, or the trace of y inverse squared times the variance of x. Again, expectation and variance are applied to x component-wise. To prove these inequalities, we will make use of the scalar inequalities, but before using them, we will need several intermediate steps. The first step is the following result. We have C, an n by n invertible matrix. We have D, which is n by n Hermitian and positive semi-definite. If we surround D by C Hermitian and C, we get a Hermitian matrix, because the Hermitian of this matrix by shoes and socks is C Hermitian, D Hermitian, which is D, because D is a Hermitian matrix, times C Hermitian, which is C. This matrix is Hermitian. It is positive semi-definite because Z Hermitian, C Hermitian, D CZ, where Z is an n-dimensional column vector. This quadratic form is CZ Hermitian, D CZ. Because D itself is positive semi-definite, then this quadratic form is greater than or equal to 0 for every Z. If D is Hermitian and positive definite, again C Hermitian DC is Hermitian. Also, Z Hermitian C Hermitian D CZ, which is this quadratic form, is non-negative. If D is positive definite, then this quadratic form is 0 if and only if CZ is equal to 0. C is assumed to be an invertible matrix, so CZ is the all 0 vector if and only if Z is the all 0 vector. Then this quadratic form is non-negative. It is 0 if and only if Z is the all 0 vector. This means that when D is Hermitian and positive definite, C Hermitian DC is Hermitian and positive definite. Consider n by n Hermitian matrices psi and phi. Psi is positive semi-definite, phi is positive definite. So phi is invertible. All its eigenvalues are strictly positive. If we take psi and surround it by phi to the minus half, we get a Hermitian positive semi-definite matrix. Recall that phi to the minus half is a matrix with the same eigendecomposition as phi, except that we replace the real valued strictly positive eigenvalues by the eigenvalues raised to the power minus 1/2. Let's assume that the maximum eigenvalue of this Hermitian positive semi-definite matrix is less than or equal to 1. Consider the matrix identity of size n by n minus this matrix. The jth eigenvalue of this matrix is 1 minus the jth eigenvalue of phi to the minus half psi phi to the minus half. Since the maximum eigenvalue of this matrix is less than or equal to 1, then the minimum eigenvalue of identity minus this matrix is non-negative. Under this assumption, identity minus phi to the minus half psi phi to the minus half is Hermitian and positive semi-definite. We also get a Hermitian and positive semi-definite matrix if this is surrounded from the left and from the right by phi to the half. This is also a positive semi-definite matrix. Doing the multiplication, we get phi minus psi. What is the conclusion? If we assume that the maximum eigenvalue of phi to the minus half psi phi to the minus half is less than or equal to 1, we conclude that phi minus psi is Hermitian and positive semi-definite. The contrapositive is that if this matrix is not positive semi-definite, which means that it has at least one strictly negative eigenvalue, then the maximum eigenvalue of this matrix is strictly greater than unity. The trace is the sum of the eigenvalues. This matrix is Hermitian and positive semi-definite. Its eigenvalues are real valued and non-negative. The sum of the eigenvalues, that is the trace, is greater than or equal to the maximum eigenvalue lambda 1. If lambda 1 is strictly greater than 1, then the trace of this matrix is strictly greater than 1. We can rewrite this result here. If phi minus psi is not positive semi-definite, then the trace of phi to the minus half psi phi to the minus half is strictly greater than 1. If we have two matrices, P and Q, P of size m by n, Q of size n by m, we have the following useful result. Trace PQ is equal to trace QB. So we can apply this here. The trace of this matrix is equal to the trace of phi to the minus half times phi to the minus half times psi. That's the trace of phi to the minus 1 psi. If Hermitian matrix phi minus psi is not positive semi-definite, then the trace of the inverse of phi times psi is strictly greater than 1. To obtain the matrix versions of the Markov and Chebyshev inequalities, we need another result. Consider n by n Hermitian matrices A and B. B is invertible. Assume that B squared minus A squared is positive semi-definite. If we surround this matrix by the inverse of B, we get a positive semi-definite matrix, which is identity minus B to the minus 1 A squared B to the minus 1. This matrix is Hermitian. Its eigenvalues are real valued. The jth eigenvalue of this matrix is 1 minus the jth eigenvalue of B to the minus 1 A squared B to the minus 1. Because this matrix is Hermitian and positive semi-definite, its eigenvalues are all greater than or equal to 0. This means that all the eigenvalues of this matrix are less than or equal to 1. The maximum eigenvalue lambda 1 of B inverse A squared B inverse is less than or equal to 1. We have 1 greater than or equal to lambda 1 of this matrix. If we have n by n Hermitian matrix omega and n-dimensional column vector Q, Q Hermitian omega Q is upper bounded by the maximum eigenvalue of omega times Q Hermitian Q. The quadratic form is lower bounded by the minimum eigenvalue of omega, lambda n of omega, Q Hermitian Q. The maximum eigenvalue of this matrix is the maximum of this quadratic form, Q Hermitian B to the minus 1 A squared B to the minus 1 Q, where Q is a vector with a unity L2 norm. We can write the quadratic form as Q Hermitian B inverse A times B inverse Q. By shoes and socks, this part is A B inverse Q, all Hermitian, times A B inverse Q. This is the L2 norm squared of the column vector A B inverse Q. The maximum of this L2 norm squared is greater than or equal to the L2 norm squared of A inverse B times any n-dimensional column vector with unity L2 norm. We choose a specific vector Q bar, which is an eigenvector of AB inverse associated with its maximum eigenvalue. So AB inverse Q bar is lambda 1 of AB inverse, the maximum eigenvalue of AB inverse times Q bar. This is the magnitude squared of the eigenvalue multiplied by the L2 norm squared of the vector, which is 1. From here and there, we conclude that the magnitude of lambda 1 of AB inverse is less than or equal to 1. If B is an m by n matrix and Q is an n by m matrix, the m by m matrix PQ and the n by n matrix QB have the same non-zero eigenvalues. Their other eigenvalues are all zeros. We can write A B to the minus 1 as A B to the minus half B to the minus half. Lambda 1 of this matrix is lambda 1 of B to the minus half A B to the minus half. Note that this is a Hermitian matrix. So if A and B are Hermitian matrices, B is invertible, the magnitude of lambda 1 B to the minus half A B to the minus half is less than or equal to 1. So identity minus this matrix is positive semi-definite. The eigenvalues are 1 minus the eigenvalues of this matrix. Those eigenvalues have a maximum magnitude less than or equal to 1. So 1 minus any eigenvalue cannot be negative. This is a Hermitian positive semi-definite matrix. Using the result on the first page, if we surround this matrix from the left and right by B to the half, we still get a Hermitian positive semi-definite matrix. Doing the multiplication, this matrix is B minus A. This is the main conclusion. If B squared minus A squared is positive semi-definite, then B minus A is positive semi-definite. Recall that we defined the absolute value of a Hermitian matrix as the matrix with the same eigendecomposition, but with the eigenvalues replaced by their absolute values. If matrix A is Q lambda Q Hermitian, then A squared is Q Hermitian on the right, and here we have lambda 1 squared all the way to lambda n squared. We get the same matrix if we square the absolute value of Hermitian matrix A. If I say that B squared minus A squared is positive semi-definite, this is equivalent to the statement that the absolute value of B squared minus the absolute value of A squared is positive semi-definite. This is because these two matrices are equal, also these two. If we apply the theorem to the absolute value of B squared minus the absolute value of A squared, we conclude that if B squared minus A squared is positive semi-definite, the absolute value of B minus the absolute value of A is positive semi-definite. The contrapositive is that if this difference is not positive semi-definite, then B squared minus A squared is not positive semi-definite. Given these two results, we can obtain the Markov and Chebyshev matrix inequalities. X and Y are n by n Hermitian matrices. X is random, Y is deterministic, X is positive semi-definite, Y is positive definite, hence invertible. What is the probability of the event that Y minus X is not positive semi-definite? In the scalar case, this was that Y minus X is strictly negative. In the matrix case, this matrix has at least one strictly negative eigenvalue. If Y minus X is not positive semi-definite, the trace of Y inverse X is strictly greater than 1. So the probability of this event is an upper bound on the probability of that event. We can upper bound the probability of the event that Y minus X is not positive semi-definite by the probability of the event that the trace of Y inverse X is strictly greater than 1. Note that this trace is equal to the trace of Y to the minus half X Y to the minus half. This is a Hermitian positive semi-definite matrix with a non-negative trace. So this trace here is like a non-negative scalar random variable. We can apply the conventional Markov inequality to upper bound this probability. The upper bound is the expectation of the trace divided by 1. That's the expectation of the trace of Y inverse X. Trace is linear, expectation is linear. We can interchange expectation and trace. In other words, it won't matter if we compute the trace of the matrix, the sum of its main diagonal elements, and then take the expectation, or we apply the expectation to each element in the matrix, then compute the sum of the main diagonal elements. When we apply the expectation, Y is a fixed matrix, so the expectation is applied to matrix X. The upper bound on the probability of this event is the trace of Y inverse times the expectation of X. To upgrade the Chebyshev inequality, we consider the event that Y minus the absolute value of X minus the expectation of X is not positive semi-definite. This event, using this result, implies that Y squared minus the square of X minus the expectation of X is not positive semi-definite. If this difference is not positive semi-definite, then we have a trace that is strictly greater than 1, specifically the trace of Y squared inverse times this matrix. Like in the Markov case, this trace can be thought of as a scalar non-negative random variable. Apply the conventional Markov inequality to upper bound the probability of this event. The upper bound is the expectation of this random variable divided by 1. Interchanging expectation and trace, the upper bound is the trace of Y squared inverse, the variance of X.